welcome to another module in this massive open online course on Bayesian MMSE estimation for wireless communication systems. So far we are looking at the MMSE, we have looked at the MMSE estimator, the optimal MMSE estimator when the parameter vector, when the parameter h and the observation vector y bar are jointly Gaussian, and we have illustrated the application of MMSE estimation in several scenarios such as wireless sensor network, wireless channel estimation, and we have derived both the estimator, the estimate and also the expression for the minimum mean squared error. So, starting with this module we will look at a different aspect of MMSE estimation, that is we will look at the linear MMSE estimator, alright. So, now we will start looking at what is known as the linear MMSE, linear minimum mean squared error estimator. This is known as the linear minimum mean minimum mean squared error estimator, okay, and this is also termed as linear LMMSE, where L is for linear minimum mean squared error, alright. So, this is the LMMSE estimator, alright. So, we will start looking at, in this module we will start looking at the LMMSE estimator, okay, and you can recall that basically the MMSE estimator, let us try recall that the MMSE estimate, the minimum mean squared error estimate. So, first we have to understand what is the difference between the MMSE and the LMMSE estimate. Recall that the MMSE estimate is given as the MMSE estimate, the minimum mean squared error estimator. This is given as h hat equals the expected value of h given y bar. This we have said is optimal MMSE estimate, okay, where h hat, remember this is the estimate or rather the MMSE estimate, this is the parameter and this is the observation vector y bar, okay. However, this is computationally computing this is a computationally complex task. Why are we saying this is computationally complex? Because if you remember, to compute this expected value of the posterior probability density function, that is expected value of h given y, first we have to compute f of h given y, that is the probability density function of the parameter vector h given the observation vector y. So, this is computationally complex because this requires evaluation of f of h given y bar. Remember, this is the posterior density. This is the posterior density from from f of h, this is the prior f of h given h, comma f of y bar given h. Remember, this is the likelihood of the observations, f of y bar, this is the probability density of the observations given that this is the likelihood of the observation. So, why is this computationally complex evaluating the MMSE estimator? Because we are given the prior probability density function f of h and we are given the likelihood, that is f of the observation vector y bar given h. From these we have to evaluate the posterior probability density function, which is f of h given y bar, which is a computationally complex task. And if you remember, we had computed this for the Gaussian scenario, that is when the single observation y and the parameter h are jointly Gaussian, and even for that scenario, if you remember, we had to go through a lengthy and very elaborate derivation, which is not possible today, and this was possible for a jointly Gaussian scenario, when the probability densities are general, when the probability densities of the parameter and the likelihood are arbitrary. In several scenarios, this is going to be very complex. So, it is not going to be possible to evaluate this posterior probability density function rather easily in several scenarios. In fact, it is computational and very frequently also intractable and often frequently impossible to get a nice closed form expression for this posterior probability density function. Therefore, we employ a simpler approach or a less complex approach or a less computationally intensive approach, which will help us evaluate this estimator, which will help us evaluate this estimate in a simpler fashion. Alright. So, we compromise a little bit on the optimality, but derive an estimate which is slightly simpler to evaluate, and that is the linear MMSE estimate or the LMMSE or the linear minimum mean squared error estimate. So, we choose a lower, therefore, we present, therefore, we employ a low complexity estimate, which is easier to evaluate or which is simpler to evaluate, let us put it that way, which is slightly simpler to evaluate, However, because it is not the optimal, MMSE estimate, therefore, it results in a slight loss of performance or slightly or yields an estimate of slightly lower accuracy, but we are accepting that because it is slightly simpler to evaluate. Alright, we are accepting that slightly decreased estimation accuracy because we want an estimate which is simpler to evaluate, and this is precisely the motivation for the LMMSE or the linear minimum mean squared error estimator. Okay. So, it is slightly simpler to evaluate, and that is precisely the motivation for your LMMSE estimate. Okay. Yeah. Now, how do we come up with the LMMSE estimator? Let us consider a scenario. Consider the observation vector y bar, which is given by, again similar to previous, we have the observation vector y bar, which is comprised of n observations y1, y2 up to yn. However, now we will form the estimate h hat by linearly combining these observations as C bar transpose y bar, which is C 1, C 2, C n, the row vector, this is a row vector, this is a row vector times y 1, y 2 y n, which is a column vector. Recall C bar is being defined as follows, this is a column vector C 1, C 2 up to C n. Therefore, C bar transpose is naturally going to be a n dimensional row vector, y 1, y 2, y n, that is y bar, this is a n dimensional column vector, this is y bar. Therefore, C bar transpose y bar, this will be naturally equal to, so your H hat equals C 1 y 1 plus C 2 y 2 plus so on up to C n y n, and as you can see this is linear because this is a linear combination. So, we are performing, so we are obtaining the estimate by a linear combination of the observations, this is, therefore, this is a linear combination of the observations, therefore, this is a linear estimate, this is a linear combination of observations. Therefore, you can see this is basically H hat equals C 1 y 1 plus C 2 y 2 plus so on up to C n y n, this is therefore a linear estimate. Okay. Now, we want to find the now we want to find the mean square error, that is MSE. So, the MSE, remember this is the mean squared error this is equal to expected value of H hat minus H whole square, expected value of H hat minus H whole square, which since H hat is equal to C transpose y bar, this is simply equal to C bar transpose y bar minus H whole square. Now, what is the key? Now, basically the idea is we have to find this vector C bar such that this mean squared error is going to be minimized. So, right. So, we are going to find C bar such that this mean squared error is going to be minimized, that is going to give us the MMSE, that is a minimum mean squared error, and now this is also linear in the observation vector y bar. So, together this becomes the linear MMSE estimator, that is the key to, that is basically the reason this is known as the LMMSE estimate. So, we have to find C bar to minimize MSE, this becomes, therefore, this becomes your MMSE, that is the minimum mean squared error, and this is also the linear in the observations y 1, y 2, y, that is linear in the observation vector y bar, therefore, this is also the LMMSE estimator. Now, since this is linear with respect to y bar, it also becomes LMMSE, that is linear minimum mean squared that is linear minimum mean squared error estimate. Okay. So, now let us simplify this expression for the MSC. We have MSC which is a function of this vector C bar, MSC, this is equal to expected value of H hat minus H whole square, which is equal to, realize that this is equal to expected value of, well, expected value of, for H hat I am going to substitute C bar transpose Y bar minus H whole square, which is equal to expected value of C bar transpose Y bar square of itself, C bar transpose Y bar minus H into C bar transpose Y bar minus H. Realize that these both are scalar quantities. So, therefore, the square is simply the quantity times the product itself, and now I am going to use a property, that is, since C bar transpose Y bar minus H is a scalar quantity, that is it is a number, basically it is equal to the transpose of itself. So, if you have a scalar quantity, basically it is equal to the transpose of itself. So, I can write this as C bar transpose Y bar minus H times C bar transpose Y bar minus H transpose, since basically this is a scalar quantity. Scalar quantity implies quantity is equal to its transpose. Okay. So, the quantity is equal to its transpose, and now we can simplify this further. Now, we can simplify this as expected value of C bar transpose Y bar minus H times C bar transpose Y bar minus H. So, C bar transpose Y transpose is basically Y bar transpose C bar minus H is of course a scalar parameter. So, H transpose is H, this is what we will get, Y bar transpose C bar minus H, and now we will expand this product term by term. This is C bar transpose Y bar into Y bar transpose C bar minus H Y bar transpose C bar. Of course, H is a scalar quantity, so we can write that anywhere, minus C bar transpose Y bar into H plus H into H, H is a scalar quantity, so I can simply write it as H square. Okay. So, that is what we have. Now, observe that Y bar transpose C bar equals C bar transpose Y bar, right. Y bar transpose C bar is a scalar quantity, correct. Y bar transpose C bar equals C bar transpose Y bar. In fact, both of them are equal to C1 Y1 plus C2 Y2 plus so on up to Cn Yn. Okay. So, these are scalar quantities. In fact, both are equal to Y1 C1 plus Y2 C2 plus up to Cn Yn. Therefore, we have Y bar transpose C bar equals C bar transpose Y bar implies, now I can multiply both sides by H, H is a scalar quantity, H Y bar transpose C bar equals, well, C transpose Y bar into H, which means now basically these two quantities C bar transpose Y bar H, right, H Y transpose Y bar transpose C bar and C bar transpose Y bar H, these are equal. Okay. So, now what we are going to do, we are going to use this principle to simplify this, and this is therefore going to be equal to expected value of C bar transpose Y bar transpose C bar minus twice, because both these quantities are equal, twice C bar transpose Y bar H plus H square. Okay. where we use the property that H into y transpose y bar transpose C bar equals C bar transpose y bar into H. Now, we will take the expectation operator inside, take the term by term expectation, that is expected value of C bar transpose y bar transpose C bar minus twice C bar transpose expected value of y bar into H plus expected value of H square. Now, we can further take this expectation operator inside, this is C bar transpose expected value of y bar transpose C bar minus twice C bar transpose expected value of y bar H plus expected value of H square. Now, realize that expected value of y bar transpose, this is nothing but your r y. Expected value of y bar H, this is a vector r y bar H. Expected value of H square, this is simply sigma H square, which we can also denote by r y, and therefore, net you can simplify this quantity as C bar transpose r y C bar minus twice C bar r bar y H plus r y. What is this? This is your MSE as a function of C bar. This is MSE as a function of C bar, which is the combining vector. Okay, so, now what have we done? We have found the MSE, that is the mean squared error, as a function of this combining vector C bar. But we are interested in the minimum MSE, that is the minimum mean squared error. Therefore, we have to find that C bar which minimizes the mean squared error, which means we have to differentiate this with respect to C bar and set it equal to 0. To find the minimum MSE, to find the MMSE, differentiate with respect to C bar and set it equal to 0. However, C bar is a vector, therefore, we have to consider a vector derivative. Since C bar is a vector, we have to consider the, since C bar is a vector, we have to consider, since C bar is a vector, we have to basically consider the vector derivative. How to differentiate this quantity with respect to the vector C bar. So, next we are going to introduce this notion of a vector derivative. So, let us consider any function f of C bar. This is f of C bar is a function of vector C bar, then the derivative of f with respect to C bar equals, well, this is equal to df by dc1 df by dc2 so on df by dcn, that is we have to differentiate the vector with respect to each component, differentiate the function with respect to each component of the vector. differentiate function with respect to each component of this vector c bar, that is basically your vector derivative. That is, if we have a function f of c bar, what I have to do is I have to basically differentiate this function f of c bar with respect to each component of this vector c bar. So, naturally I am going to, if c bar is an n dimensional vector, because I have to differentiate with respect to each component of c bar, I will get basically n component. So, the vector derivative is naturally will be going to be an n dimensional vector, because it is a vector containing the different components df by dc1, df by dc2, so on df by dcn. So, naturally this is going to be an n dimensional vector. This is going to be an n dimensional vector. Alright. So, we are going to consider the vector derivative, which is an n dimensional vector. Alright. So, let us stop this module here. What we have started looking at, we have started looking at a different paradigm or a different framework known as linear MMSE estimation. So far we have looked at MMSE estimation, which we have said is very complex because it requires the evaluation of the posterior probability density function. So, in order to avoid that complexity, what we have done is we have started looking at this linear MMSE expression, that is the linear minimum mean squared error estimator, which involves this vector combining vector c bar of coefficient c1, c2 up to cn. Using that, we form the LMMSE linear estimate c1 v1 plus c1 y1 plus c1 y2 plus so on cn yn, which can be represented as c bar transpose y bar. Now, we have to find this optimal vector c bar, which minimizes the mean squared error, that gives us the MMSE minimum mean squared error, and therefore, since this is linear in nature, that will become the LMMSE estimate. Alright. So, we will stop here and we will complete this derivation of the LMMSE estimate in the next module. Okay. Thank you very much.